Well, let's begin. This lecture is on quantum mechanics to some extent because I want to explain to you not quantum mechanics, but again, how we have been coping with various ideas as we've made progress. Now, some physicists believe that we know all the basic rules of science pretty well. There's nothing really mysterious and missing. We know electromagnetic, gravity, and all the other primary forces. And we think we know something about the intermolecular forces and the nuclear forces. On the other hand, they've had to admit that something like 90 to 99% of the matter in the universe they don't know anything about. Calculating one way, there must be a great deal of mass in the universe. Counting everything they know, they find they're missing something between 90 and 99% of the mass. So physics doesn't know everything yet. The question is, how much do they really know? Now, you should understand one thing. Science never tells you why. It tells you what. Newton's law of gravity told you how something fell. Indeed, it was in connection with gravity that Newton said, I don't make hypotheses. I only can tell you how it acts, not why. Nor can I give you the details. In fact, Newton did not believe in action at a distance. He thought it was ridiculous that any sensible person would believe that two things could interact when they were separated. Well, you've gotten used to the idea. You find nothing strange about the sun's gravitational field affecting the Earth, and the Earth's gravitational affecting the moon. You are used to the idea now, but in Newton's time, that was not really considered sensible philosophy. Now, at the end of the 1800s, near 1900s, physics was going quite well, and people were rather smug about what they knew. But there were some symbols indicating that things were not right. For example, spectral lines occurred discrete things, but all the physics they had was continuous, smooth variation. There was the black body radiation, which is, given the temperature, what is the distribution of frequencies of the radiation. And you know when you heat up a rod, it's dark, becomes dark red, it gradually moves up to white heat. It's the color changes. That's changing the distribution. As a function of temperature, what's the distribution of light emitted by a radiating body? The ideal one being a black body. Well, they had a theory which fitted at one end, but gave infinity to the other end. They had a theory that fitted the other end and gave infinity to the first end. It was unsatisfactory. Max Planck fitted the data with a curve. It fit beautifully. He said to himself, this fit is not chance. There must be a reason behind it. There must be a theory by which I can deduce this distribution. So he set out to try and find a theory. He had a great deal of trouble. Sooner or later, he latched on a method which you know from calculus. You divide the thing up into a finite number of pieces. You take the sum, and then you take the limit as the largest interval goes to 0. Well, he tried that with the energy. He broke the thing up into a bunch of little energy sizes, and then tried to take the limit. Every time he took a limit, the distribution disappeared. When he left the limit to find its size, he had a distribution. In fact, the size he left it finally was Planck's constant. He found apparently that energy occurs in pieces, discrete hunks, because that was what fitted it in. He delivered this thing around Christmas vacation in 1900. It didn't really catch on for a long while. Einstein connected with the photoelectric effect, which is you shine light on a metal, and when you get to a certain frequencies, the metal will emit photons or electrons, otherwise will not. They were sharp things. And he again used this quanta, and that began to get people interested in quanta. And we had the old quantum theory, which tried to account for things. The quanta were emitted discrete pieces, and Bohr made a strange model looking very much like the solar system, tried to account for the spectral line spacing. Now, those spacing have been known for mathematical reasons. We really found formulas that fitted the distribution of lines for various materials. And they fitted quite well when we tried quantum mechanics, but it lingered around until well, let's back up. When an electron moves in a straight line, you're all right, but if it bends around, it's supposed to radiate. And we produced this experiment in the lab, and sure enough, it radiates. But in the Bohr model, the electron was running around, it should have radiated, and it should have collapsed like that, but obviously the molecules of the world are pretty stable. Otherwise, you wouldn't be here. So we had a large number of troubles like that. In about 1925, two people started in with new ideas. Heisenberg started with the idea that Einstein had once believed in about only dealing with those things you could measure. So he started writing down arrays of spectral lines that he could measure and other such things. And he produced a quantum mechanics, which was surprisingly good, all things considered. Schrödinger, on the other hand, thought about waves and produced the wave mechanics, which were differential equations. Now, you've had enough mathematics to remember matrices have eigenvalues which are discrete, and differential equations have eigenvalues which are discrete. So both theories could account for the discrete nature of the spectral lines and various other things which have been coming up slowly in quantum mechanics. Schrödinger and Karl Eckert, showed that these two theories, much as they differed, were equivalent one to another in the sense that you say the high school geometry you learned, Euclidean, and analytic geometry are equivalent. You can prove a theorem one way or the other, but in fact you can't. Some theorems will be proved both ways, but sometimes the analytic method is the only way you're ever going to get a proof, and sometimes the synthetic one is about the only one you're going to do. So yes, they're equivalent, but no, not quite. And in fact, shortly afterwards, Dirac came up with some generalized Q vectors, which were very generalized from what Heisenberg had done. And there was also a group theory approach about the invariance of this and that. So there were a number of different approaches to quantum mechanics. But different as they were, they accounted for the same things. Now I want to dwell on this point. I've said it last lecture, I said it one time earlier still. You can have different theories which account for the same phenomenon. Given phenomena, it is not possible to go to a unique theory. No way. It just doesn't work that way. Now let me discuss how Planck's experience affected my career. I said to myself, Max Planck found something fitted very, very well, and he was led to a significant result. When I calculate for people, let me calculate in terms of the functions which they could understand, for which they might create a theory. Let me not fiddle around with these dumb polynomials that most of numerical analysis and statisticians use. They seldom, if ever, have any physical meaning. So if I'm going to do some calculating for somebody, what I go do is go to lunch with him and talk about the kind of functions he believes in, the kind of things he thinks apply to his field, and then try to calculate in those kind of terms, hoping that if I get a spectacular fit, the man will do what Max Planck did and discover something great. Well, I never had that greatest success. I did, however, get some scientists to see much more in their field than they had by using the appropriate functions. Thus, history, because I want to be associated with great things, affected the way I behaved. I behaved so I thought I may have a chance to be associated with something great, such as quantum mechanics. Well, I didn't hit it, but I did some good things. So this is an example of what I'm trying to teach you. You look at the world, how it behaves, you say, oh, that's the way great work is done. Let me behave that way. Maybe I will be involved in some other great work. Now, to illustrate this matter of not having the same explanation, from the data, get back to the theory, at one point around here, a student quarreled with his professor very badly, and I took over running a PhD thesis. I found that he was measuring, using random input, measuring various outputs and trying to establish correlations as to the structure of what was happening. Thus, you might very well have a chemical plant. You look at the inputs, you look at temperatures and so on, and you try, from looking at the output, deduce what is the equivalence network theory structure of the chemical plant. I found that it was well known, meaning almost nobody bothered to mention it, but it was true, that there could be very different electrical circuits giving exactly the same output for the input, that they were theoretically indistinguishable. That's another example I'm saying. You cannot, from data, go to a unique theory. Much as you might want to, it isn't possible. Therefore, if somebody has some ideas and you have some ideas that are quite different about the same thing, it does not follow that either of you are wrong. The theories can be different. Now, the real quantum mechanics dates from about 1925. Has had tremendous success. It's more successful probably than any other theory when you consider how many small detailed things it has successfully predicted. It's amazing. Now, the trouble with quantum mechanics is that we are large animals, and quantum mechanics is concerned with very small details of atoms. You're not used to it. They don't behave necessarily the way big things behave. Therefore, the way we think doesn't seem to fit the way quantum mechanics behaves, if you believe quantum mechanics. You see, our ways of thinking obviously were part of evolution. Those ways of thinking which did seem to match the big material world which you lived in meant that those ancestors survived and were your parents. Those who didn't think quite so straight weren't your ancestors. So naturally, the kind of thinking you can do comes from dealing with a fairly large world. Now, the situation was that Newtonian mechanics, which you're familiar with, accounted for an enormous amount of details. It predicted unknown planets. It predicted a great many unknown effects. Polarized light was predicted successfully. Nevertheless, at both ends, it didn't fit. At the high end of large masses, great velocities, and great distances, relativity took over, special theory and general theory. At the very small end, quantum mechanics took over. So a very, very well verified theory over hundreds of years, from Newton's time to practically around the early 1900s. It reigned supreme, it fitted everything, and yet at both ends it was wrong, in the sense that it doesn't really predict as well as the newer theories predict. Now, Newton thought, more or less, now he was pretty cagey when you read him. He thought that light was particles because light goes in straight lines. Now, he knew that there had to be some wave-like motion because he knew about Newton's rings and other things, but somehow light had its fits. It fitted together sometimes, so reinforced, sometimes it was dark. So he knew about this, but he seemed to have favored, as you read him, he is favoring particle, but he doesn't really say it must be. He merely uses it a lot because light goes in straight lines after all, and particles go in straight lines. Waves don't seem to. Nevertheless, in time, wave theory replaced particle theory for a long while. It's very likely the optics you learned if you took optics courses was based on wave theory, that light was wave motion. And like waves in the ocean, if you have very small opening, it spreads around, but if you have a very wide one, the waves tend to go fairly straight. And in fact, around an object, you will find diffraction rings of shadow behind it. And you will find a remarkable prediction that if you take a coin and shine light on it uniformly, there should, in the exact middle of the black, a small white light spot. And you can find it if you search hard enough and look with adequate equipment. So a prediction made was found to be true. Now, the thing that happens is that we now tend to believe, and quantum mechanics asserts, that things are neither waves nor particles, that both the wave theory and particle theory were partially right. And what comes about is that you sort of see the particles when the light falls on a photographic plate. It falls right there and develops that grain. But it also has a pattern. The two-slit experiment, you remember, you light through two slits and you find a wave-like pattern depending upon the spacing of two slits. But the photon must have gone through one of those slits and not the other. But then how could that wave pattern depend upon the width of the thing? So you say, well, you know, it was a wave and the wave went through both slits. But somehow that wave became a particle when it hit the photographic plate to develop the grain. So light is a wave and a particle. It's both and it's neither. Now, since 1925, this has been more or less accepted belief. And since 25 to 95 is quite a few years. And every professor of quantum mechanics has said in one way or another, I cannot explain how it can be both a particle and a wave. You'll have to get used to it. And it is surprising, as you work long enough with quantum mechanics, you do get used to the idea that things are neither particles nor waves, and they're both. It's not a thought that you can think very well, and let me make a slight digression to give you something to think about. You are familiar there are smells that dogs cannot, the dogs can smell and you can't. You're familiar that various birds can see frequencies of light you can't see. There are certainly sounds, high pitches that dogs can hear and you can't hear. And there are some tastes that some people can taste, other ones can't. So there are stimuli which you cannot detect, being built the way you are. Why do you get mad when I suggest that your mind's wired the way it is? There are thoughts you cannot think. And I suggest you a candidate is the wave-particle duality. Our mind wasn't wired that way, and we have enormous trouble trying to think of how a particle will wave and a particle at the same time. Now, the original stuff was more or less light, which you think of waves as particles. But Davison and Germer at Bell Labs shot electrons at a grating and got diffraction just as if it were a wave. And it's been generally accepted that the Davison-Germer experiment, for which Davison got the Nobel Prize, did in fact show that particles look like waves, as well as waves look like particles. That they're just dual things of the same thing. Well, this has produced an enormous sea of mysticism. Bohr is, I think, the reason why there is what is called the Copenhagen interpretation of quantum mechanics, named really after Bohr, because Bohr had an institute at Copenhagen which was well supported, and practically every early physicist went through the place and spent some years there at one time or other. Bohr was really a Vienna positivist at heart. And he explained things in what is called the Copenhagen interpretation. There is not one unique one, but it's a general philosophy about the wave-particle duality and complementarity. The wave and particle are complements of each other. You look at it one way or you look at another. You can't look at them both at one time. They are complementary descriptions of the same thing. And generally he produced a lot of mysticism about how many things in fact are complementary. You describe it one way, you describe it another. And while they conflict, they don't. You use one way and one another way. Thus, this tabletop, I would regard the class of elasticity as being solid. In a class in physics, I'll say, well, almost all that tabletop is empty space. There's just a few atoms and electrons scattered around thinly in the whole place. They differ. We use them different ways. It's not always accepted. The original founders did not accept the Copenhagen interpretation. Schrödinger, Heisenberg, Einstein particularly, but de Broglie and Pauli and others, all of them more or less rejected the Copenhagen interpretation, which is, however, the dominant religion. It's, as it were, the Catholic religion of the Middle Ages. You're a Catholic or you're out. Well, that's about the way it is in physics. There are heretics all around the place, a guy named Bohm and various other ones, and I happen to be a heretic too. A lot of us who are heretics who don't quite believe the Copenhagen interpretation, because it's got a lot of mysterious things. For one thing, the whole idea of what the particles were in a matrix or the wave, Born declared one day, oh, the square of the wave function really the absolute value of the square, is the probability that it will be someplace. And the same way, the square of the components of the matrix, which were complex numbers, were the probabilities, meaning the intensities of the lines. Unfortunately, as you look at it, you don't know what they mean by probability. And there are two different things, at least, in probability. There's the probability of the unique event, and there's the probability of a whole bunch of events. So you typically think probability is the ratio of the successes to the total number of trials when you go to infinity. That's the typical one. But you see, that doesn't fit the one I told you about calculating the probability the bomb will set off the atmosphere. Come on now, you don't get a frequent number of trials. You either do it or you don't. So it's clear that the idea that probability is a limiting ratio of repeated trials will not fit many, many situations. And our boy Dirac observed that when one photon goes through the two-slit experiment, it interacts with itself, not with any other photons. Because no matter what the light intensity is, you get the same pattern. If you go so low a light intensity that by and large there's only one photon in the apparatus at a time, you still get the pattern. So it's clear the photons are interfering with themselves, not with the other photons running through the thing. So it's pretty clear that they ought to be interpreting the probability in quantum mechanics as being the probability of a unique event, not an average over a large number of trials. But you can read quantum mechanics and you have people flopping back and forth from one description to another. It's very badly muddled up as what they mean by probability. It's a very awkward subject. Now, when I say Born did what he did, and what I say Schrödinger and Heisenberg did, they were feeling their way forward. They did not know what they were doing. This is the way a new theory comes up. It explains a few things, and you hope they'll explain more, and you gradually build up and develop. They developed the theory. They didn't know, and I told you a moment ago, we really don't understand it anyhow. Nevertheless, we are able to use it. And this is one of the points I want to bring up. Even if you cannot, and our minds are not wired to understand some phenomena, that does not mean we cannot build a mathematical structure which will enable us to predict reliably. That's roughly what we've done in quantum mechanics. You get used to quantum mechanics, but under pressure, almost everybody, Feynman certainly, you just have to accept some things you can't understand, namely the wave-particle duality. After that, the rest goes along, but you don't really understand that. So, something we can understand, we have nevertheless built a theory. And that bears on your future. I've told you repeatedly that my predecessors at Bell Labs did the easy problems. It seems to me we did the moderately hard ones, and we left the worst ones to the people who come afterwards. We've done most easy problems. As you attack more difficult problems, it's going to be much harder. Take, for example, the understanding of the human mind. You presumably have some electrical engineering. You know one technique. Break the thing up into black boxes, and with comparatively few interconnections, one can do the analysis of a complicated network circuit, provided there are not too many interconnections. If there are too many interconnections, you're going to have trouble. The other approach we have is if a thing is highly repetitive, such as in statistical mechanics, we can build up a theory which tells you how it will behave. Well, the brain obviously is a very complicated thing. If it were highly regular, we could perhaps go at it through statistical mechanics. And if it were a block here and a block there and a block there, loosely interconnected, we can go at it the way we do circuit analysis. But all the evidence is that it's neither. Yes, speech is in some region, but it's connected quite intimately with large other regions. There aren't any nice separable parts, much as we wish there were. There are some regions which seem to do some things, but you want to be careful. If you are talking to your mother in New York and somebody in Kansas cuts the telephone line, one doesn't conclude that the speech is originating or being processed in Kansas. It may be only the transmission line. The habit of thinking that the mind is where the thinking occurs is very, very widespread. But it may only be the communication channel, because there's one terrible fact. You can take one-celled animals and train them in the sense that after a while they will go down this thing and turn right rather than turning at random. Well, a one-celled animal hasn't got a nervous system, but it can learn. Therefore, all learning does not occur in the nervous system. In simple, very simple animals, there isn't a nervous system to work with. It must be done some other way. So we really don't know much what we're doing. We tended to think that the nervous system, the connecting wires of the telephone company, is a telephone company, rather than asking more the question, isn't it really the people talking to the people that matter, rather than the telephone line connecting it? I don't know. We don't know. But you're going to work in these more complicated things, because we've done the easy problems. And so one of the things you have is you may be able to build a mathematical model which will work fairly well predicting without genuinely understanding. And if you produce a model and somebody says, well, what's the meaning of this? You say, I don't understand, it doesn't matter. It successfully predicts. It's not satisfactory, but that's what we have done in quantum mechanics. We've done it since 1925 at least, if not 1900. We've done exactly that and got away with it, more or less. Now, because we had probability in quantum mechanics, there was the immediate hope that below what we could observe, there was a deterministic where we were only seeing the random results of it. But below it was deterministic. Well, von Neumann proved that there were no hidden variables, as it were. There was nothing regular beneath it. But it was found the theorem was not really proved, so somebody else proved it. There has been a sequence of proof and disproof of hidden variables. The chief one, still dominant, is there is nothing below the probabilistic version of what the wave function tells you that probably this particle will happen or probably that will happen, but there is no mechanical thing below that which has got definite. Now, they can't prove it because any proof of that kind of thing must rest on a large number of other assumptions. You don't prove something with just a few assumptions. So they have this awkward thing of trying to believe that below, at the very bottom of particles, there's an essential randomness in the universe. Well, it's not too widely accepted. On the other hand, the philosophers tried to jump on it and conclude that that was where free will lay. After all, if molecule bangs on molecule and everything is predictable, where's this free will, all the other things you think you got? Well, I wouldn't bet on using quantum mechanics to produce any free will at all, although the latest book by the guy in England, he wrote The Emperor's Clothes, and he's written another one, tries to somehow or other connect the uncertainty in quantum mechanics up with freedom of your action. It doesn't make sense to me, but he does like it. So you have a problem of whether there is freedom of choice, whether the world is in fact random or whether it's deterministic. You can pick what you want. We have no way of proving anything. It is a religious question. And it's a religious question for a number of reasons. Most religions have a God which punishes you for ill and rewards you for good. But if everything is perfectly determinate, you only could do what you did. There wasn't any free will. What's this God who's punishing you for doing what you had to do? It's not too popular. Therefore, if you're highly religious, you just don't care for the idea that the whole universe is completely determinate. Even if there are randomness at the bottom, there's no free will or anything else like this. It's kind of hard to reconcile. On the other hand, there are other sides that are equally hard to reconcile. For example, the other side, God being infinitely merciful. This was pushed to the limit by one of the Buddhist sects around 1000 AD in Japan, the Amida Buddha, which if I had to choose a religious sect, I'd pick that one. The general belief was the Amida Buddha was infinitely merciful, and if when you died, no matter how evil a life you led, if when you died you had to appeal to the Amida Buddha, you will go to Western paradise immediately, no question. After all, God was infinitely forgivable, infinitely merciful. It doesn't matter what you did, He would forgive you. Well, you can see the problem religions have between these various things, and you can see how what you're going to believe in quantum mechanics will depend to a great extent upon your view of religion. Now, religion is a very strange thing. In organized religions with a high degree of structure, if you want to listen not to your religion, but listen to somebody else's, you will get the impression sometimes that the priest or the minister has got a contract with God, and if he delivers his part, God's got to deliver his part. Certainly in one religion, which I was a consultant for a while, it's pretty clear that if you give enough money and they do enough religious things, your grandmother will now go up to heaven immediately. Contract job. You will find a fair number of people say, well, we will do so and so, and then such and such will happen. We will pray for you and you will be saved. One religion, originally, the Mohammedan one, Muhammad, knowing this, was annoyed, to say the least, and he said, you as an individual face God one-to-one. There's nobody between you and God. That's part of the reason why the name comes. You face God directly, and you just ask God, what is it, God, you want me to do? There's no negotiating in the original. Well, organized religions generally get some negotiation in, so they will have a position, and this is what you find in most religions, sooner or later, a good deal of structure which doesn't fit in too well with the founding fathers. The Buddha, again, wanted no part of having an organized church. The Buddhist religion now is highly organized. And the Christian religion is much different. You remember Christ didn't go along too well with it, got thrown out of the church because he didn't really behave himself properly. Well, he didn't think too much of it, but we've now got a great hierarchy. So all religions tend to do this, and it comes down to this problem. It's not separate from quantum mechanics. Your religion will, to some extent, determine what you will believe about the world. Now, I'm not condemning it. What you believe about the world may influence your religion, but it's very likely to be a religious question of how you will react to quantum mechanics and various things said. It's a very, very awkward question when you come down to it. Now, I personally do not believe it's worth arguing freedom of will or any other things based upon our current beliefs of quantum mechanics. I think the attempt to argue about how God or the world is, that part of the world, your relation to God, that part that you should try to argue on the basis of science currently believed, doesn't seem sensible to me at all, because we're going to change our beliefs about our current science, and it ought not to be that if we change our idea of science, God changes. It doesn't seem likely. Well, they're in a stuck position then. If you believe the materialistic world, how do things that are non-materialistic affect the motional molecules? How do ideas? Or how does God come in and affect the motion of molecules? So that instead of this happening, that will happen. When I took psychology course back in the 30s, the problem was, one of them was solved by what they call psychophysical parallelism. There was a physical world and a psychological world, and the statement was made that these two go on parallel tracks. There's no interaction, but they perfectly correspond. That seemed absolutely ridiculous to me at the time. But you are faced with this problem. If you think there are these two different things, how does this materialistic world change because of this other world? Where is the interaction occur? How does it occur? Is it limited to you, or does it also apply cats and dogs? Do they have free will? Does a mouse have free will? Does a worm have free will? These are awkward questions, and they have best answered not by appealing to quantum mechanics, but appealing to what you believe, because it's probably just as likely or better. Now, quantum mechanics got worse. A guy named Alain Aspect in Paris did some experiments. You send off a particle this way and a particle this way, and we believe they have spins in opposite directions. This way, but it might be plane, but whatever polarization this one does, that's the opposite. Now, we also believe in quantum mechanics that the measurement determines. Before then there's a probability distribution, but the measurement puts it in a definite state. Thus, the thing had a probability distribution. When the photon finally hit the photographic plate, the probability distribution collapsed to 1 point, and it hit right at 1 point. Well, we make this measurement 6 meters up. Instantaneously, this is found in the opposite. Not with the velocity of light, but instantaneous. Now we set the equipment up so that after they're separated, only then do we choose which way we'll set this one to measure. This will be found in the opposite state. It violates, in some sense, relativity, which says you can't signal usefully faster than the velocity of light, but then that's not useful signaling. Apparently it's not. In fact, when I heard Elaine Aspect talk one time in Chicago, there was a question afterwards about what relation does that bear to relativity, and he said, I'd rather not discuss the question. And I've kicked myself ever since for not raising my hand and said, why don't you want to discuss it? But I didn't, and so I don't know why he doesn't, because it's a very awkward problem. Now, I can swing a searchlight so fast that the end of the beam is moving faster than the velocity of light, but that doesn't mean I can communicate from there to there via that beam. I can go from here to here, but not from there to there. So that things can go faster than the velocity of light isn't really too bad, but it's bothersome. This kind of experiment, which they call entangled, once the two parts are entangled, they had a common source, they are now connected, and something here will affect that instantaneously. Well, that says something happened on Mars. Instantaneously, it has its effect here. Two particles, once connected, entangled, are permanently entangled, and one behavior can instantaneously be transported to the other. This is action at a distance, but it's non-local action. We've been used to the idea that if something's going to happen here, the effect has got to come through, and I can catch the effect before it gets here and measure what it is. No, this happens instantaneously. Einstein did not like that one bit. He got his buddies, Podolsky and Rosen, they wrote the EPR paper, in which they tried to show there were some limitations of the kind of things you could measure and produce some inequalities. And these led to a guy named Bell producing some much more serious Bell inequalities, which quantum mechanics has to obey. You can't have every possible measurement. Only some kind of thing is going to happen, if that's true. But this instantaneous action at a distance is disconcerting to most of us. I find it very disconcerting. Very. Things across the universe instantaneously. It happens there, a million light years away. This other one responds the other way immediately. The one you measure one set there, the other. Now, is it true that the wave, the measurement sets the distribution? This is the belief. And in fact, the belief goes further. Generally, in the Copenhagen interpretation, you have to have some conscious mind measure. Some consciousness is required to set the wave function. Well, if you can believe that typical interpretation, then I say to you, from the Big Bang until consciousness arose in the universe, the whole universe could be in no particular state, because it doesn't settle down to a state until it's measured by some conscious mind. Well, that doesn't go with me as well as you either. So, although that's the official doctrine of measurement, that the measurement is not fixed until someone conscious measures it and sees it. Doesn't go. In fact, Schrödinger, one of the founders, invented a cat. He has a cat in a box. He has a detector for an electron coming by from some radioactive particle with a 50-50 chance. And if the particle goes by, the Geiger counter trips, the poison bottle is open, the cat's dead. If it doesn't trip it, the cat's open. Well, official quantum mechanics says the cat is neither dead nor alive until you look. That's the famous Schrödinger cat. You can see that we're not in very good shape in quantum mechanics. It is the dominant theory. It's the only one we got. It's doing very well. But philosophically speaking, it's got a large number of things to give you a headache, to say the least. Now, besides the Elaine aspect, one of the other non-local effects and such things now, I don't pretend to understand and particularly the word understand. I am in the same position I told you St. Augustine around 600 AD. St. Augustine says, I know what time is until you ask me, and then I don't know what time is. I think I know what understanding is. I think I know I understand something until you ask me. I cannot write a program which will do understanding or cope with a thing. No way. I haven't a glimmer of idea of how to write a program which can cope with the word understand. Yet I'm reasonably confident that I understand some things. And you are reasonably confident you understand some things. Well, we're in a bad way. We don't really know what we're doing. It's a very vexing problem we're in. Now, I've been trying this course all the way along to get you to realize that while science has been very, very successful in many areas, it's not the end. I recall in the case of simulation, I told you very carefully, if I have a simulation and the simulation says A, and some expert who's got a lot of experience says, no, that's not right, what do? I've worked out my philosophy. If it's a slowly changing technology, I bet on the person with experience. I got great faith in intuition. If, on the other hand, it's a rapidly changing technology, I bet on the simulation. Because intuition is based on the past, and we're moving in a different world. Very different world. And that's the problem you will face continually. You would like to proceed scientifically. Science is never going to give you exact answers. In spite of the DNA trial stuff down in Los Angeles, science never really proved anything. And I'll give you a talk on it one day about what science does and doesn't do under the title of epistemology. What the hell can we know, what can't we know? We really don't know. But you came through evolution, or God put it in you, either way you want, with a hell of a good intuition, provided the intuition was built up in the circumstances you are now operating in. If it was built up in circumstances which are different, then of course the story is quite different. The intuition is counterproductive. And I saw that enormously with my predecessors who were successful doing mathematics one way, and they knew computers were no good. They did 1,000 things to one way or another oppose the oncoming of computers. And at lunch today I discussed with the ex-dean how much still this school is resisting the obvious fact that machines are around, they're going to be around permanently, and why the hell don't we get used to the idea? Why don't we, for example in calculus, adopt what was available in '60? Programs which will do all that damn analytic integration and algebra, everything else. They're around, they're available. The original paper was written by a blind programmer. Well, I can't think of his name, I know the guy quite well. And when he wrote the program and did it at MIT, it was as good as the undergraduate at MIT, and it was about as cheap, using the old Whirlwind, which was an expensive machine. Machine costs have come down, the programs have got better. Now, such programs of analytic integration will beat any undergraduate in speed, cost, range of application completely. Why are we still doing the old things? I don't know. We have not really come to terms, but society cannot flip-flop overnight. In sympathy, we are already living through chaotic times. We've got enough chaos now. Nevertheless, it seems to me that we have been rather remiss at adopting and coming to terms with what the machines will be. I keep saying by 2020, laptop computers with enormous memories of all kinds of stuff should be readily available to the student. You should be able to walk into class with your little laptop computer and enough stuff there for the content of all the textbooks you'll be using that term, if not all the textbooks you'll be using while you're here, along with all the techniques and methods right on there. So you can call them up. Punch differentiation, there it'll be. Punch integration, there it'll be. We ought to be somewhere near there then. We could do it. Whether we should or not is another problem. And I waffle. Some days I think there's something we miss, and sometimes I think, well, maybe we do have to go slowly. Now, we're moving also into another area which you're going to be worrisome. We are beginning to be able to hold a single atom right there and know we've got one atom right there. Up until very recently, we couldn't. But we're beginning to do this. Well, when we can get a single atom and we can tag it, say we put it in an excited state, and we ship it through a two-slit experiment, we should know whether it went through that slit or that slit by where the emitted particle comes from. And so this uncertainty principle comes out of quantum mechanics. Isn't so good. It isn't so good at all. We may be able to measure whether that theoretical thing that we cannot know position and velocity, which I put in the notes on digital filters, is nothing more than a Fourier transform theory. A theorem in Fourier transform says the variability, second moment, of a variable times the variability of its conjugate variable, this Fourier transform, must exceed a fixed constant. Well, that's exactly what you have in quantum mechanics. The uncertainty in the position multiplied by the uncertainty and the momentum must exceed a fixed constant. They are the conjugate variables. The Fourier transforms one of the other. It's strictly a mathematical theorem. It arises because you have a linear theory. Every linear theory must have an uncertainty principle. We put what we see in quantum mechanics, we put it in there when we created a linear theory. We have put a lot in of what we now see, more than you think, much more. And so the world is rather difficult. And what we're learning gradually is we're learning, I'm going to repeat this quite a few more times, we are slowly, as we come to terms with computers, learning about ourselves. Physics began as remote as it could from us. We've done pretty well with those things. We're simply being closed in more and more on ourselves, and I've been preaching at you. Your education was bad. You were told too much about the external world. You were not told enough about human beings, but human beings are the heart. Morale is the heart of your business. Human beings are the heart of your business. I've often said I'd rather have a high morale team than have real good weapons. The best weapon I can give you cannot compensate for low morale. No way. It's far more important. But we're giving you here mainly a course in hardware, partly because we know how to tell you that. We don't know how to tell you the other things. So we tend to tell you what we know. But I've done this course. I've deliberately told you a great many things that I don't know. I've been making you think about it. I told you frankly, I am not going to give you answers. My job is to make you think. So we'll see you again next week. Thank you, sir.